Director of SIMIODE and Emeritus Professor of Mathematics from Military Academy, USA. And he's going to talk about in support of modeling first teaching of differential equations.
Thank you. Can you hear me?
Yes,
Good.
thank you so much.
Well, thank you for welcoming me to Canada. I have visited your beautiful country many times, especially when I was a graduate student at the University of Buffalo, when we would routinely cross the border and come back. I'm particularly honored to be speaking at a conference with regard to Ada Lovelace. Of course, she was a prodigy and a forward-thinking woman, and on computing and some stuff on codes and ciphers as well as a dear friend of Lord Byron. So thank you again. I want to talk about in support of modeling first teaching of differential equations. A little personal information never hurts. I started out as an undergraduate and I was headed to the Lutheran ministry. I was going to be a missionary and go to Africa and save the world and get a medical degree and cure all the ills and bring everybody to Jesus. Obviously, that changed when I hit college and started to enjoy mathematics, and my theology wavered. I was the organist at chapel. I did lots of tasks. I went on to graduate school and I got a PhD in Noetherian ring theory from Professor Azumaya at Indiana University. However, when I started teaching in 1971 at Albion College, I discovered modeling with mathematics by visiting the science library. In graduate school, the math library was pretty much theoretical, and I never went to the regular library. But when I got to teaching in a small liberal arts college in a faculty of 4, I visited the library, the science library, which was in our building, and I saw all this mathematics and biology, chemistry, physics, ecology, even economics in that science library. And I started to be fascinated by it. And I'll mention a little bit more on that. But I've taught in Research One universities, at Brown universities, engineering colleges. I've taught at the U.S. Military Academy, where the Army is. I've taught at the Air Force Academy. In 1977, I founded a journal on codes and ciphers called Cryptologia, and it's about to be 50 years old now. It's been edited by a young colleague. I founded a journal called Collegiate Microcomputer and killed it when every discipline had its own computer journal. There was no need to have a broad-based one. More recently, in 1990, I founded a journal called Primus, Problems, Resources, and Issues in Math Undergraduate Studies. Both Primus and Cryptologia are freely offered to members of the Math Association of America. With your membership, you get access to all these 30 and 40 years of journals. Finally, in retirement, I formed SIMIODE, which is the Systemic Initiative for Modeling Investigations and Opportunities with Differential Equations. Initially, I poured lots and lots of my retirement funds in there. And if the words like divorce and I will leave you had not come up in our household, I probably would have still been pouring my own money. But in the interim, we became a nonprofit. We received National Science Foundation funds, and we have 3 sustainable efforts. Let's just talk about my own discovery about the models with mostly differential equations that I discovered. And the world changed for me. I became more of an applied mathematician. I taught abstract algebra, but I never published papers in that area. I wound up publishing lots of papers on teaching in applied math and differential equations and founded those journals. I did return to algebra when I was editing the Cryptologia journal. Obviously, cryptography has a lot of discrete mathematics and lots of algebra and field theory and so forth. Okay, So what I want to talk to you today about is 3 modeling applications and sources that you might find in addition to the one that I had up. Um, we are free. All the materials are free. We have 3 sustainability efforts. One, a modeling first textbook, which is HTML based. It's $39 US. You can get the paperback with print on demand as well as the HTML for $89 US. And you can learn all about that at the website. So I don't want to spend my time promoting that, but that helps pay the technical people that run the web page, and it pays rent because our community sits inside of a broader community called Cubes, and we contribute to their technology. We have a conference that comes up in February. It's called Expo. It's in its 5th or 6th year. And this year it's devoted strictly to class activities involving modeling in a differential equation course. Of course, differential equations come up in calculus, but they also come up in modeling courses. They come up in statistics courses for stochastic methods and so forth. And finally, the third effort is SCUDUM, and that's SIMIODE challenge using differential equation model. And we're just about wrapping that up. It's now in its 10th year. Teams of 3 students pick one of 3 problems. And again, all of this you can see at our website. You can see all the past problems. You can see the top student awards because they present 10-minute videos and they're judged by international judges who volunteer their time. Okay, so I want to talk about these 3 modeling activities. The first one is modeling death and immigration using M&Ms. You don't have to use M&Ms. You could use coins or little chips from Monopoly or games like that. The second one is modeling a falling column of water. The third one is modeling LSD drugs from data from the 1960s from Harvard University. So let's get going. This perhaps is one of the most widely used modeling activities found in SIMIODE. Thousands and thousands and thousands of people use this activity. Many of them use it in the first day. So let me just tell you what we're going to do. You have to have 2 cups, one with some initial amount of M&Ms, and a sheet which has generations. And what we're going to do is toss the M&Ms into the plate, and if an M shows up, that M&M dies. So you toss them out, and if an M is face up, you remove that M from the population. You take the remaining M&Ms, you put them back in the cup, and you toss it again. So what happens is, if you just did that, they would die off exponentially. Now, the students don't know that term. They don't know any of that if you do it on the first day, and they can collect that data, they can plot it, they can find the exponential decay. And you and I know that if you kill off an M&M because its M shows up on top, you lose about 50% each generation. So your decay rate is 0.5, and you can estimate that with data. It won't be exact because this is a random process. So here are the rules for a little more elaborate one. So you put about 25 M&Ms in a little cup. You toss them gently. Don't toss them rather wildly. They'll go all over the floor. The first time I ever did this, I never had a plate. So we tossed them onto the desk and they were all over the floor and getting dirty and everything. But you toss them onto the plate. You remove the ones with an M facing up, they die. You add or immigrate 10 M&Ms from your extra pile that you have. So what are you doing? You're dying or you're killing off M&Ms and you're immigrating, okay? So you ask the students then to count the remaining at each generation and you store the data. You record the data of how many at each generation. And what you do is you go back to step 1, you toss, you count, you immigrate, and you just keep doing that, okay? So here's a spreadsheet with this, and all of these resources are in the SIMIODE web community. And there are teacher versions of all of this material that are only available to people who identify as teachers. And then there are student versions for the public to look at. Everything is free. The teacher versions of everything, almost all are in LaTeX. Some are in uh, a Word. There's maybe a dozen in French, a few in German, one in Czech, none in French so far. But this is an example of a spreadsheet that is available for teachers to either demonstrate, or students can construct their own. So here's the model. What happens is you lose half if B sub n is the number of M&Ms at generation n. You get the number at generation n is cut in half, because approximately a half of them die, and then you add 10. So this is a difference equation. And in the modeling activity, we call these units modeling scenarios, and there are hundreds of them in SIMIODE, and you can look them up by keywords. They're all free. And as a teacher, you can download it, you can modify it, you can customize it and make it your own. And also there's a section in there about how you convert between difference and differential equations. And many teachers have written me saying they really like that part of the modeling activity because they don't concentrate on that much in class, and textbooks don't. Anyway, so here's the sort of the ideal model. You have B sub n, you get about half of them left, and then you immigrate 10 and you iterate. Here's a more general model. We don't know what the death rate is. We have an idea, but we're not sure. It could be 0.48, could be 0.52. And the immigration could be 9.3, could be 11, but we knew from what happens that it was 10. And here's another model where we absolutely know it's 10, but we don't know quite the death rate. So here's some data. This is the actual data in underneath insert your data. We had 50, then we went to 40, then we went to 32, then we went to 26. Remember, each generation, we basically cut it in half and add 10. Cut it in half, add 10. Here's what a perfect model would do. We have 50, it would drop to 25, you add 10. 35, you would drop to 17 and a half, you would add 10, et cetera, et cetera. Now, obviously, these fractions of M&Ms are not real, but that's the numerical work. So here's the difference between the model and the perfect data. And you can see that it is, what we're doing is we're taking the sum of the difference squared. And what we're going to do is what students have learned to do in high school physics lab, minimize the sum of the square errors. So here's some data with 2 parameters, and here's some data with 1 parameter. And this number is the sum of the square errors. If we assume that we immigrate 10, and just guessing, we assume that the death rate is 30%. In fact, it's more close to 50%, okay? So you can go into Excel, and all of this is explained in the activities that are freely available to you. And we use the solver command. Now, I find that when I do workshops, and I do lots of workshops, lots of faculty don't know about solver. So if you're taking any notes, just write that word solver down and look it up in Excel, and I'll show you what it will do. What it will do is, if you specify parameters A and B, it will find the best fit parameters which minimize the sum of the squares automatically. And it will fit that model as best it can. Let me show you a result. After using solver and getting a model compared to the data, here's what the model says. It says you should have a 37.5, et cetera, et cetera, et cetera. And here's what the data is. So it's pretty close. And after a while, the students will realize where this is headed. It's headed down to 20, which is an equilibrium value. By the way, one of the values of this lesson on the first day is it introduces many, many vocabulary words like equilibrium, steady state, um, difference equations, differential equations, solving, fitting, etc. And one of the things you could say to yourself, if you, and the students will do this, they'll say, you know, if you had 20 and you lost 10 because they died off, and then you added 10, you should come back to 20. And if you have 20 again and you lose roughly half, you get down to 10 and you add 10. You should get back to 20. What they just discovered was equilibrium value, but they didn't know that word. And then you tell them that's an equilibrium value. So you can do all of this and they can have success and enjoy this. And they will refer to this activity at the end of the semester. I've had colleagues write to me and say in course end evaluation, they said the best activity was on day one when we did the M&Ms, not just because they ate them, which they do, but because they saw all these concepts. So I urge you to look at this activity. Again, everything is free and you can see it in its entirety and you can change it. Here's another one with M&Ms. This leads to the logistic equation. Oh, one other thing with this, you can give each student their own set of M&Ms and you can say, why don't you decide Andrew may immigrate 12, Lynn may immigrate 8. Each student will immigrate their own, and then you ask them to pass their data to their neighbor. Then the neighbor has to determine the immigration level from just the data. I've done that, and that's very rewarding because they don't know the answer. When you do this in class and everybody immigrates 10, they go, yeah, 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 it's 10. Well, when you get your neighbor's data, you don't know that it's 10. Some people only immigrate 1. Some people immigrate 20, etc. Okay? So here's another model. You get, and we have this sheet of paper, and you can print these out. It's printed on squares that are exactly the same diameter as an M&M. And you mark about 8 of them with an X. You pick them randomly. They all have a disease. All right, a very, very transmittable disease. You take about 50 M&Ms, a small bag, and you throw them onto this array. Usually I put books around the edge so they don't go off the table. And what you do is if an M&M touches one of those squares, it becomes ill, okay? And then you write the number. So for example, when I did this iteration, an M&M fell here where the number 1 is, and it touched the X. So number 1 became infected. From there on out in the experiment, that number 1 was infected. Here's number 2 became infected. Number 3. Then maybe I picked them all up and I tossed them again. Now number 4 became infected. More and more and more infecteds. Nobody leaves and becomes cured. All we're doing is passing the disease. It could be a short-term disease. We have a cold, something. Doesn't have to be something dramatic. When you collect that data, you can do the same thing. Here's a logistic model. And again, this is introduced in the material on this modeling activity in SIMIODE. And you have a parameter. So you have the logistic equation, and here's the solution. And here's the data in blue. Or here's the estimate, and here's the actual model. And when you fit the data to the model is in red and the data is in blue, you get a pretty good logistic fit. It's quite reassuring. Again, this is deterministic. I mean stochastic. So it's not going to be perfect, okay? So let me go through another one. And by the way, all of these slides will be posted with the video, so you can refer to them. This one, we have videos on a falling column of water. Each video has an iPad with a digital clock, and you can start and stop, start and stop. You can collect data on the height in centimeters. Um, and you can write down the time. So this is a 2-liter bottle, and we have a hole in the bottle, and the water is leaving, and you're trying to model how fast the water falls. What can you do? Well, you can see, and each student can collect their own data. We have lots of bottles and models and videos on our YouTube channel, and you can get to that easy by going to YouTube and just typing SIMIODE, and you'll see our channel. They can conjecture empirical models. We'll do that. They can build an analytic one from first principles. That's what you'd really like to do by creating a differential equation. They can solve it, they can estimate their parameter, and they can check with real data. Okay, so here's some data that I collected. I collected at time 0, it was 11.1 centimeters high. At time 2.187, it's 10.6. This is an iPad, which gives you time to the nearest thousandths of a second, which is really crazy, but that's what it does. So here's all the time. Here's the data. You're in Excel. Excel has trend line. First inclination is to use some of the functions that are there. So one of them is, let's slam a straight line through it. Is that a good model? The answer is not bad, but it doesn't bow, it doesn't bend, and it's kind of straight. And some of the students will say, you know, it looks like it's falling faster at the beginning than at the end. And other students will say, yeah, that's because you got all the water on top forcing it out. So they're doing a little physics here. Next, we might try exponential decay. Not quite that good. Remember, this is a physical model. We don't have randomness here, so we expect, if we get a model, we expect it to be pretty good, and that's not pretty good. So these are all empirical. They're attempts to just fit the data, no explanation. Can we get something better? One of the things we then do is say, can we find out h of t, the height at time t? And the answer is that could be hard, but could we find out how fast it's falling? And maybe from there, back out what is h of t? That is, could we build a rate equation and then find h of t? So here we make some notes. We find out that initially it's falling at the rate of 0.22 centimeters per second. But towards the end, it's only falling at the rate of 0.12 centimeters per second. That kind of makes sense with our intuition. It's falling more rapidly and slowly. Okay, so let's try and get some first principles and solve this rather than just slam some data. The material that comes next is from Evangelista Torricelli. He was a student of Galileo. He invented the barometer, and he had a wicked, wicked mustache, which I think is way cool, okay? So now you can do one of two things. I'm talking to you, and I'm going to tell you what Torricelli's model is. If you don't want to do that, you can develop it. So here I'm telling you what his model is, and we'll develop. Some classes, we don't tell them, we just develop it, and here it comes. But here's what Torricelli came up with. The rate at which the height falls is proportional to the square root of the height. And that kind of makes sense. When h is big, the square root of h is big. When h is small, the square root of h is small. There's a g in here for the gravitational acceleration on Earth. Obviously, if we did this on Pluto or Jupiter, it would be quite different. And then there's a b in here, and that's kind of like a coefficient that absorbs information about viscosity. If we're doing this with motor oil versus water, the thickness or the opening in the hole, the nature of friction, etc. And so let me just go on. And what we're going to do is quickly use the law of conservation of energy, which says total energy is conserved. And again, all of this is in the materials online for the teachers. And what we measure is the total energy of a slab of water at the top and a slab at the bottom. So we get the total energy is kinetic, which is 1/2 m initial velocity squared plus the potential, which is mass times gravity times the height, etc. If you have physics students in class, they're comfortable. If you don't, then you got to make them comfortable. And one way is to say, please accept this. Let's see what it does for us. So you begin to build the model, and what you get is the final velocity of the water at the bottom, at the hole, is equal to the square root of 2GH. Okay. And you can start now and say, could we solve that? So when I did this in class, it was the first time we did separation of variables. We had a reason to want to solve this differential equation, and that was the motivation. This talk is about modeling first differential equations. You saw the model, now you see the solving, okay? I don't want to go through this, but what you get eventually is a model with one parameter. I knew the G, if I'm in Colorado in the United States or in Banff, it's different than if I'm in Nova Scotia on the shore. And so how do we estimate the parameter B? Well, by now I've done the M&Ms, so I know I'm going to use the sum of the squares. And I have a big mess. This expression, if I did it in Mathematica, which I use often, is about 2 pages long. It's 9 data points, equations and everything. But here's what we have using the sum of the square errors. Here's the data in blue. Here's the model in red. And if we hit the solver button that says, give me the best fit coefficients, here's what we get. The first time I did this on my own before I went to class, I panicked because one of the data sets got lost. But it didn't get lost. The red and the blue dots are exactly on top of each other. Why? Because this is a physical model. There's no randomness in here. And so it's a perfect fit. Okay. This is a model of the flow of LSD between tissues and blood. And they got students at Harvard in the 60s to sample LSD, and they measured how much was in the blood by sampling their blood over 8 hours. They can't determine how much is in the tissue because they can't inject into your brain and examine. But what this model allows you to know is if I can tell you how much is in your blood, I know how much is in your tissues. And what they get is a model because they have a system. It's a linear system for the concentration in blood and so forth. And in Mathematica, you can solve that. This is what you get for all the parameters for the concentration in the plasma. And the beauty is that here's the data for one patient, and here's what the model predicts. Pretty good, don't you think? But more importantly, you can now infer how much LSD is in the tissues. And you can
I
see that it's high.
apologize, Brian. So
That's want to
sorry.
stop. That's fine.
Yes, please. Like 1 minute. 1 minute, please.
So anyway, one of the things you'll see is that model, but let me just go to the end where I'm telling you about all these resources. Here's some examples. At the end, I wrote a paper on how you get resources. And here's example after example of where you can find modeling activities. Okay. All of this is on the slide. You can look at them. I want to thank you for your time. If you're going to do modeling in class, don't do too much at once. Start slow. One time I had a colleague say, what models could I use? And I sent him a list of 10. And he wrote back, how do you do all 10 in one period? And I went, oh my goodness. You just do one. And here's another approach. And I share this paper with you. It's in the British Journal. Have the students be a consultant. This is a fabulous way to get them involved. You become a client. They are a consultant. They have to get information from you. And any calculus problem would do, any model would do. So I want to thank you.
Thank you so much for your inspiration talk.